Hi, my name is Bill. Welcome to Probability and Statistics for Everyone. And welcome to video 2.2, where we will continue to explore the difference between probability and statistics, while simultaneously highlighting the relationship between them. So let's get started. This is a direct continuation of video 2.1. So we'll start by recalling the last technical screen from that video. In the upper left-hand corner, there's our combined definition of probability and statistics, which I'll recall for you now. In the presence of randomness, probability is the science of prediction and model development, while statistics is the science of data description and inference. We'll continue to open this definition up in this and subsequent videos. But for now, let's go ahead and clear up some screen space. On the left, we have our Notional Probability Lab. And in that lab, we consider the random outcome from rolling a single six-sided die, which we presume to be fair, meaning each side was equally likely to land facing up. We developed a mathematical model for the probabilities and represented that model in both equation form and graphically. On the right, we have our Notional Statistics Lab, and in that lab, we considered a vase with chips in it. From that vase, we randomly pulled 10 chips out of a reported 40 and came up with estimated general probabilities of drawing a green or yellow or red chip from the vase, while we presumed, based on the 10 we drew, that there were no other colors in it. We then estimated the number of each colored chip remaining in the vase after those 10 chips had been drawn out. Now, I wasn't as careful in the previous video as I should have been with my statistics lab notation. Actually, it should have looked more like this. For one thing, I will typically try to color code my notation so that black is used for general or deterministic information, blue for probability-related expressions or plots, and red for actual data and statistics of the data. I've also added the explicit notation that the chip count estimates, those are the n-hat equations in the bottom, are based on the 30 chips we expect to still be in the vase after we've taken 10 out. Now that I've cleared that up, let's go back over to the probability lab and let the probability lab use all of the screen space for a while. We're going to reset our example of rolling a single six-sided die, including by expanding out the equation form of the probability mass function, or PMF, to separately list out each possible outcome. Our presumption of a fair die is asserted in this model, which indicates that the probability of any one of the 6 possible outcomes is equally 1/6. Next, we'll roll the die one more time. We see that this particular outcome is 4. We've circled this outcome on both the plot and the equation. Next, we'll add a second die and roll the 2 dice together. We'll also present an updated model for this 2-dice example. We won't go into detail about how we develop the model in this video, but the key assumption is that as the 2 dice are bouncing around in the coffee mug and then rolling around on my breakfast room table, the individual die outcomes are not coupled together in any way. That is, one die is going to bounce and roll and land however it lands, and the other one is going to bounce and roll and land however it lands. The 2 die outcomes are independent of each other. Now, the reason we did this, the reason for showing the model for something as seemingly haphazard as the sum of rolling 2 dice out of a mug, is to remind us that probability is the science of prediction and model development. It is our declaration that we can model what is possible and impossible from rolling 2 dice and describe how probable each of those possible outcomes are to occur. I want to pause and repeat that. With the science of probability, we often can describe what the eventual outcome is from internal or intermediate random phenomena. We can add a third die and roll the 3 dice together, but we also present the 3-dice model. We can add a 4th die and do the same. That is, once I actually get all the dice into the mug. 4 6s. Now that is unusual. In fact, our 4-dice model indicates that there's only a 1 in 1,296 chance of getting that on any single roll. It's actually good that that came up while recording. What we have just demonstrated is that even the very improbable outcomes do actually occur. We'll continue on by adding a 5th die and rolling the dice, indicating where that outcome is located on the 5-dice model. We could keep adding more dice, but that's not really necessary. All I wanted to demonstrate was that a mathematical model was possible for each case, and to show where on the model each outcome was located. Let's go back to the case where we have 3 dice. We're going to roll those 3 dice 5 times and record the sum of each roll. For each recorded value, we'll place a red arrow on the probability plot to indicate where that outcome is located on the 3-dice model, together with that particular outcome's probability. Once again, I'm doing this to ground the elements of the probability model to physical outcomes. But I'm also laying the foundation for building the bridge between probability and statistics. You see, these individual probability values that we're enumerating now are typically not what we're directly interested in when applying the science of probability to problems in statistics. But they are building blocks for what we are interested in. A probability model can't predict what any particular outcome of random phenomena will be. That is, for example, it can't say exactly how a die will land on any given roll. But it can predict what an ensemble of multiple outcomes will tend to become as those outcomes are accumulated. For example, if we roll 3 dice 5 times, as we're doing now, what do we expect those outcomes to tend to be? In that sense, we can begin to talk about typical outcomes from a random process. To aid in the discussion, we'll introduce the notion of the center of a probability model, which is that value that separates the model into 2 equally probable halves. This particular model has a center of 10.5, which is readily apparent because it has the added feature of being mirrored or symmetric on either side of the center. We can visually see this symmetry on the plot, and we're reorganizing the equation form of the probability model to group the values that have the same probability together with each other. Notice that the center itself is not one of the possible values. After all, 10.5 is an example of otherwise. Another feature of this particular model is that the more probable outcomes are near the center, and the less probable outcomes are further away. For example, even the values 9 or 12 are less probable than the values 10 or 11. That pattern won't always be the case, but it is here, and we're going to take advantage of that as we consider the notion of a typical outcome. We're going to begin by considering a proposed definition of typical as being a roll of either 10 or 11. What would be the probability of this composite outcome? The answer is found by adding the 2 individual probabilities together and coming up with a value of 0.25, or 25%. I'm going to ask you to trust me on this. We'll explain it more fully in a later video, but because the outcomes 10 and 11 are mutually exclusive, meaning they can't both occur on any one roll, we can add their probabilities this way. Now let's pause and consider this definition of typical that we proposed. If it's an outcome that only occurs 25% of the time, that doesn't seem like a very useful definition of typical. So we'll expand our definition to include any of the values between 9 and 12. Again, we add the individual probabilities and discover that this candidate definition of typical will be expected to occur almost half of the time, which is better but still not as useful as we want it to be. We can continue to expand our definition of typical one symmetric pair of roll possibilities at a time and see how our composite probability grows. Of course, our definition of typical eventually expands to a probability of 1.0 or 100%, which is too large because it means that there are no atypical values. So what's a good definition of a typical value? Well, it depends on why we're asking. That is, it depends on the application. For now, we'll select those roll outcomes that are near enough to the center so that the probability of the included outcomes adds up to around 95%. For this model, that means including the rolls 5 through 16 and excluding the rolls 3, 4, 17, and 18. If we now overlay the outcomes from the 5 rolls that we recorded earlier onto this plot together, we see that all 5 of them would be considered typical by our current definition. How would we respond if one of them had been atypical? Like those 4 6s we rolled earlier. Surely, that outcome would have been considered to be atypical in that 4-dice model. Well, again, that depends on the application, and we will get into applications in later videos. In this video, though, we're only going through some probability exercises to lay a foundation for later demonstrating how probability is typically used in statistical applications. Having done that, we find ourselves at the end for now. It's time to leave the probability lab, where we have spent most of this video, and reconsider the task at hand. We are exploring the definition of and difference between probability and statistics. In the next video, video 2.3, we'll go back into the statistics lab and consider those colored chips that we're pulling out of a vase. So keep coming back.